Okay, so now we go to the bigger questions that have probably been burning on your mind is let's say you're given a vector field. Now let's just say that, the first component of your vector field, let's just call that capital P. And then the second component is capital Q. So whatever it is, right? Like, for example, if your vector field that you were given was, let's say, xy squared, and then you had over here x plus 3y, then this would be P and that would be Q. That's all. Okay. So if you have this, you could also, of course, write P times vector I plus Q times vector J, either notation. Then, if you're given a vector field, and we've called the components now capital P and capital Q, there are two questions that I think you really, really have in mind. One is, how can we find out, or how can we check if this given vector field is conservative? I think that's an important question on people's minds. And then, if you do know that f is conservative, so if f is conservative, is known to be conservative, then you probably want to know how to find a potential function. Right? How do we find a potential function? Potential function lowercase f. That is, we're looking for an f where the gradient of lowercase f is equal to the vector field that you're given. So both of these questions are interesting because the first question, is capital F conservative? That'd be helpful in figuring out if you don't have to compute the integral the traditional way with the dt thing. Of course, that option's available if you like it, but we also want to know sometimes it's just easier to use the fundamental theorem of line integrals. So can we do that? That theorem requires having a conservative vector field. So then second, let's say we find out, the problem allows you to use the fundamental theorem of line integrals. Well, you need a potential function. You need a lowercase f. So how would you compute that? I think these two questions are very natural, and we've set up well for the need to answer both of these questions. Well, here's the way we're going to answer it. It's a little backwards, but let's just start with, let's just say you had an f that is conservative. So if the f you're giving was conservative, if f were conservative, then there was a scalar function behind it, right? There was a scalar function, or scalar field, if you'd like to use that name, scalar function or scalar field, lowercase f of x comma y. And what would have had to have occurred would have been that the gradient of f, which, by the way, right, would be the partial derivative of f with respect to x, comma let's write that better, the partial derivative of f with respect to x, comma, partial derivative of f with respect to y. This would have to equal the vector field, which, by the way, was capital P, capital Q. So what we would have to have occur, just matching the pieces up, this has to equal that. I know this doesn't seem very profound, but let's just mention it, that that partial derivative of f with respect to x would have to equal capital P, and partial derivative and q would have to equal partial derivative of f with respect to y. Now, one thing to recall from way back when was that Clairaut's theorem. Guaranteed the following thing, namely that if you start with a function f and you differentiate it with respect to x, and then you take that and you differentiate this with respect to y, that has to equal, if you start with your function and differentiate with respect to y, and the result of that, and you differentiate it with respect to x. So you differentiate once with respect to x and once with respect to y. This theorem, just as a reminder, in other notations would be f sub xy is equal to f sub yx. Now, because that's true, because this would have to be true, if a little f existed, okay, then take a look at this. We'll replace what's in parentheses here with capital P, and we'll replace what's in parentheses right here with capital Q. Capital Q. So, here's the theorem. It answers this question of how can we check if f is conservative. Okay, so the vector field, capital F, a two-dimensional vector field with components capital P and capital Q is conservative if and only if. Okay, so this if IFF means if and only if, and we just really copy this. It's partial derivative of P with respect to y is equal to partial derivative of Q with respect to x. Okay, so if you have a conservative vector field, this equation has to be true, and if this equation happens to be true, then you have a conservative vector field. That's the if and only if. This goes both ways. So let's now take this theorem here and apply it so we can practice this theorem on a couple examples.